All right, how's everybody doing? Everything's pulling up. We'll give it just a second. Yep, all right, so for today, we are going to be covering how to field troubleshoot automation devices of different kinds. So we have several different controllers here. We also have a couple of different types of like relays. We have some thermistors, different types of actuators. So I will give a live demonstration using a voltage generator on a digital input actuator, along with kind of give you some examples of what a floating point can do, and even actuate that to kind of give you some examples of just what that looks like. So we'll get into it today. Ultimately, really big things to understand whenever you are going into when you're going into troubleshooting field devices is you have a controller that is the primary brain of whatever system that you're working on. Now, typically, in most buildings, you're going to have one controller per, like, say, piece of equipment. So let's use, for an example, we have a chill water air handler or, say, a VAV or fan power box out in the space. Each one of those individual pieces of equipment are going to have a controller similar to this, you know. So we really need to start to understand how to look at these things, how to troubleshoot them, and even beyond that, a lot of the equipment that we're going to be working on as time goes on is going to have some kind of DDC control. It's direct digital control of some kind. Now, these particular ones are PLC styled, where they're programmable logic controllers, so we can actually write code for these and make them do what we want them to within, you know, certain tolerances. Whereas, you know, a lot of the equipment, even on just the most basic of residential systems, you can still buy them that's just a freaking capacitor and a contactor, sure. But a lot of them that are going out, especially heat pump, you know, that little solid state controller, most of the time, even just regular heat pumps, they're not solid state controllers anymore. They're full-fledged little microprocessing boards with logic and temperature and everything built into them. So they're actually thinking about what's happening, and that's all these are doing. To kind of give you a quick rundown, so any basic system or board is going to have a lot of the same individual components. So you've got the main processor, you've got a bunch of IC controllers, which are integral controllers. They basically do nothing more than just support basic control functions for the microprocessor. What everybody is usually the most interested in is your inputs, outputs. So you can see over here, I can tell you by looking at the design that this particular side has, these are going to be analog inputs or outputs of some style. These particular ones are probably going to be outputs. So over here, I can tell you that these terminals right here are going to be binary outputs specifically. The reason I know that is because they have a little triac on there. So these triacs, these are the new relays of today. You know, none of these controllers up here even have actual relays built into them. Just making sure this Honeywell doesn't. Yeah. So none of these actually have it. So this is a JCI or a Johnson Controls controller. We've got an Allerton here. This is a Honeywell, and this is a Distech. So you could see any number of these, and there's a lot more than this that you could run into. And I'm not going to go crazy into all the little bitty nuances of this. My point is just to kind of give you some understanding of what this looks like and you know, just the differences. The biggest thing that's really different about modern controllers versus a lot of your older style, these cannot handle loads. So a lot of older controllers that had legitimate relays in them, they actually had the capacity to where you could support some kind of minimal load through there. You know, that might mean a contactor coil for a set of heat strips, or that may be, you know, maybe you've got 2 or 3 contactors wired in series, or not, wouldn't be series, but in parallel with each other, and that's engaging, you know, stage 1 of heat. And that wasn't that big a deal on older controllers with actual relays, because they were nothing more than this, just about that size. They were little bitty micro, tiny little plastic boxes on those control boards. Well, triacs do not have the same current duty that we were able to get with you know, those relays. So triacs, they need to be pilot duty devices only. So, for example, these particular relays have next to no actual coil load, meaning that when they're energized, you're not even going to be able to read any kind of current through this, whereas a larger traditional contactor coil, you will. You know, it's going to draw a lot more current through it, and especially if you stack multiple of those together, you're going to get a lot more current. So that's the difference. And so many times we use these for ISO relays or isolation relays. Ultimately, on your binary outputs, for example, so they're going to process through these triacs right here. So this is a Distech. These little black boxes right here are going to be your triacs coming to this output here. And it's actually numbered. You have DO1, 2, and 3. So these need to be feeding the coil voltage right here, which is, on this particular one, yes, 14, 13 is pretty standard numbers. These triacs need to feed through this coil. Feeding through this coil is not going to put enough load on those triacs to inevitably create a significant failure. It's just, they can handle that. I would not trust those triacs over a long period of time on anything other than this. And even having multiple of these ran together, I don't even know that I would trust that. When I say that they are very minimal in the load they can handle, I really mean that. You also have to be careful. You have universal inputs and outputs as well. So universal inputs and outputs, which are going to be these little circuits, they also have little transistors and triacs in them as well. But I don't know how well you can see that here, but these big black boxes are your full-size triacs. These are dedicated digital outputs. That's all they do. They're just, they complete the circuit. There's not a contact that closes, but the protons in there complete the circuit and allow the electricity to flow through. And over here, this could be outputting an analog. Actually, no, these are universal inputs. Either way, these could be inputting an analog signal of some kind, or they could be inputting some kind of, you know, just straight, like a, gee whiz, like a status, for example. You know, say a CT relay closes and it completes the circuit. So you have to be even more careful with universal inputs, and you can have universal outputs, because they have even less current duty rating than a dedicated binary or digital output. So just things to keep in mind as you are troubleshooting these things. Moving on to kind of give you just a basic rundown of a typical controller. So this is a Honeywell. This should be a Spider series, where you've got the main control module and then you've got the actuator attached. Now, this would be something you would put in like a VAV box or a fan power box, and the vast majority of the time, these are going to be a floating point style control. So when you have floating point, that means that we are we're modulating the position of that actuator. This is also a floating point, BLEMO. We're modulating the position of that actuator by sending pulse signals to the little motor. So the motor you see right here, these are the same thing, just two different brands. I can't open this one because it doesn't really go back together all that well. But that little big silver round thing in there, that is your motor for the actuator. So you can actually see the little shaft spin in there whenever you activate it, and you can watch it turn. So anyway, this all of these floating point actuators are rated in a position that they can float to. So for example, this one is specifically 95 seconds. So what that means is that if this actuator is at 0%, then if I put voltage to, this would be 24 volts to terminal 1, and this one doesn't say, it should be terminal 3. Anyway, if I put voltage to terminal 1 and terminal 3, I need to apply that voltage for 95 seconds, we're talking 24 volts, for that actuator to fully cycle over to the 100% position. And then when I stop that voltage, it's there, it's done. Now, if instead I didn't want, if I didn't want 100%, then I could split that 95 in half and say I just give it a 60-second pulse, which I know is not half, but you get the idea. Then that actuator will move, and once it hits 60 seconds and I drop the voltage, it's going to lock into that position, and it's not going to go any further. And it's just going to wait for me to send another voltage signal back to it. Now, so if I did it that way, to rotate it back counterclockwise, I would have had to have put voltage on terminals 1 and terminal 2 at that point. So terminal 1 on this particular one is your common terminal, and then 2 would be like your counterclockwise, 3 would be your clockwise. In contrast, this Honeywell, all you have is your, let's see, they kind of have a similar setup. So terminal 1 right here, this is your common, terminal 2 is your clockwise, and terminal 3 they have registered as your counterclockwise according to this one. So this is the same actuator, you know, just I have one taken out, taken apart. When you're troubleshooting these, typically floating point actuators are very, very simple and genuinely easy to troubleshoot. So for example, if we take our meter, most of the time, and I'll test it here, we can test between our pins and see our motor resistance. So I'm going to go between the common and the counterclockwise and see if I can get any resistance. Now, this may not work, and I'll explain why in a second. I'm just curious if it will. So it does. So if I go between terminals 1 and 3, I see 486 ohms. If I go between terminals 1 and 2, I get 490 ohms. And that's what I would want to see. What I just read is the stator on that tiny little motor. And those should be identical. Now, I don't know what the factory tolerance is on that motor, so I can't tell you that. And it's going to be different actuator to actuator, so don't think that 490 is the go-to. Now, the reason I wasn't 100% sure if this was going to work is you see this little brown clay thing in there. That is a capacitor, and its specific job is current overload. So if something happens and this thing pops, surges, whatever, that little capacitor may be what pops and stops the current flow. Now, one thing really neat about Honeywell's is there's another little pin connector you can unplug. And what you're seeing there is now you have 4 little wires coming off of that to that green connector. And these 4 wires run straight to the motor. The reason there's 4 is because that's 2 different stators. And we can test it here in a second to see which stator is which. But we have 3 wires coming into the main controller, or into the main plug, because the 2 common wires on the stator are tied together. So they share the same terminal point coming in and out of the actuator. So if you ever questioned, okay, well, is there an issue with that little capacitor possibly? Well, you could do literally what we're doing now. Pull this little green pin off and then test between it. I got to see which one is which. Not that one. There we go. So terminal, say 2 and 4 is one stator. And then terminal 1 and 3 is the other stator. And I got the exact same readings.
It's a little hard to see with your fixed setup.
Yeah. Yeah, hopefully y'all can follow along as best you can. I am limited in how well I can make the camera work, but everybody here, y'all get to at least have it in your hands. So, anyway, that is just another way of testing actuators. Now, my question I have for you, what type of device is this? In terms of an automation system, what type of device? What types of devices do you have? Inputs, outputs. So what kind of device is this? It's an output. So let's go through what some of our inputs and outputs could be. Yep. So on our inputs, you can have temp, you can have humidity, which these are 2 different styles of sensors. You could have pressure, current. It could be just any kind of status closure, is whatever type of relay, so for example, you have a current relay or you have a current transducer, right? So current could come through 2 different ways. So if you had a current relay, then the clamp would clamp around, say, the common leg or L1 of whatever motor you're trying to get a status on. The magnetic field off of that motor would be what activates that relay's coil, if you will, right? So it's using that. So most of the time a current relay is set to activate at like 1/2 amp or a full amp, depending on the size and style. And then all we're doing is we're just closing a set of contacts inside that relay, and it's good, it's activated. Whereas a current transducer is actually able to vary many times like an output, or vary the milliamps going through it based on how much current it reads. So the reading through it will change as it sees the magnetic field increase or decrease. So you have a couple of different types, or ways of doing current. Pressure is also done in multiple ways. So, for example, these would be air pressure pickups for static, static pressure. But ultimately, you could have a legitimate transducer. A 0 to 5 volt or most transducers are actually 0.5 to 4.5 volts. So that could be feeding back to the controller on an analog input, activating it. So anyway, yeah, pressure, current, yeah, that's really most of it. So you could say stuff like, well, you could have status or things, but that goes back to, you have some kind of current relay or some kind of interlock relay. Some basic outputs would be a relay of any kind. You could have a reference, and that's exactly how that's spelled. If you're spelling it a different way, you're wrong. So reference, when I say reference, that can mean multiple things. It's kind of a broad term. But I want to be very specific with using that term because a lot of devices, I'm seeing manufacturers use that more and more consistently, especially when you start dealing with VFDs. So a lot of VFDs, you have a reference point coming into it. That reference is your input signal. That's your speed signal, if you will. And at the same time, this is a digital input actuator, meaning that I need to send this thing 24 volts on one set of terminals, and I need to give it a 0 to 10 volt, right? This one's 0, yeah. I need to give it a 0 to, no, this one's 2 to 10. I need to give it 2 to 10 volts DC in order for it to pick the position. So right now, it's in a 0 position because I'm not inputting anything into it. Is after I give it, say, 10 volts DC, it's going to move into a 100% position. So that is the reference feeding into this actuator, just like we would feed into a VFD. At the same time, there's a fourth terminal up here. That is a reference signal coming out. And I'm pretty confident if you look up the literature on this, it's actually going to refer to that as a reference. That reference is actually a potentiometer of some sort inside of here that is sending a position signal back to the automation. So at that point, your first 3 terminals become output terminals, or really terminal 3 is your output signal coming from the controller. But terminal 4, well, it technically says 5 here, but that fourth terminal is feeding a signal back. Instead of it being an analog output from here, now all of a sudden we have an analog input as well. And we're able to map that signal to a position. And honestly, well, I'm not going to go down that road. That's what reference is. So when we start talking, having a reference, that is typically an output of some kind. But it can, I could technically make it an input, but yeah, anyway. So you have some kind of relay that you're firing. You could have some kind of reference point. Relays could do literally anything. I mean, just whatever a relay you can put on a relay, whether it be a heater, whether it be a fan, whether it be a valve. Yeah. So, yeah, we'll move on. This is not an exhaustive list, by the way, just in case I'm just throwing that disclaimer out there. The other critical thing to make sure we understand is if I can spell analog now, right? And there we go, analog. There's an A in there. You have analog and binary / digital. I did make it to the 3rd grade. I'm not going to say if I made it past that, but I at least made it that far.
Still gonna spell digital wrong too?
Digit. Yeah, I'll get there eventually. Tall. All right. Binary digital, same thing. Usually referenced as a B or a D. What, I still spell it wrong?
No, you got it right.
Okay. Stick in your head. Usually referenced as a B or a D, so that is just manufacturer preference. I'm trying to see if JCI specified. I got the cover somewhere else. Right here. How did JCI say it? So JCI says out. Just O. Okay, well that's less helpful. Honeywell references it as a digital. Distech says digital. I know that you'll run across some of them. They'll say binary, so just take that for what you will. Point is, these are the same thing. So analog is a varied signal of any kind, meaning that it has a 0 and a 100%, and it can be anywhere in between at any given time. So whether that's 1 volt DC, 2 volt DC, 5 volt DC, 10 volt, whatever. A digital or a binary, on the other hand, is one or the other. It is either all the way open or all the way closed. Relays count as a digital or binary type device. It's either open or closed. There's not much of a way to make a relay kind of in between. At least if you ever figure out how to do that, you probably did something wrong. Maybe a chatter, there we go. If you make a relay chatter, then you've now created an analog relay. Because then we're doing pulse width modulation.
Then you got an SCR.
Right? See? Yeah, there we go. We got SCR. The SCR is a type of digital relay. No, analog relay. There we go. Yeah. Not really. I guess that does kind of bring up an interesting point. So I think most everybody is pretty familiar with the analog signals are typically, a varied voltage, most common 0 to 10 volt DC, I think is the vast majority of what you're going to see out there. At the same time, it could also be a milliamp signal, so a 4 to 20 milliamp. And actually, I meant to grab a relay, and a resistor, realizing I forgot to. It's okay. If you have a system that's running a milliamp signal, and you need to convert it to a 0 to 10 VDC, this is something that ABB used to have us do. I think they built it actually into the drives now or something to that degree. Anyway, you can take and put a 500 ohm resistor between the input and common or ground terminals for a milliamp signal and convert that signal into a 0 to 10. So if I would have remembered to get the resistor, I could show you that. So I'd be able to put my signal generator in a milliamp mode, and then I could put the resistor in series, in parallel. The resistor would go in parallel. And then I could take a reading, and because normally on a milliamp signal, you'll read some kind of weird standing voltage, right? Even though the milliamps are fluctuating, I think it'll be something like 20-something volts DC, typically. So if you walk up and you're testing and you kind of see a weird 20-something VDC signal or voltage somewhere, then you likely are seeing a milliamp. So if I then turn around and put that resistor in the circuit in parallel, that 20-something volts would then all of a sudden, it would be a 0 to 10 volt somewhere in the middle, and I would be able to see that 0 to 10 ramp up or down. So anyway, those are the two most common. Now transducers, so most of the time if you're working on a transducer on any kind of piece of equipment, those are typically a 0 to 5. So just bear that in mind. And binary is pretty well open and close. We already covered that. The one thing that a lot of people may not be as familiar with is a PWM. So you have PWM. That is pulse width modulation. This technology is widely spreading throughout the industry in several different ways. So it is definitely inside of building control systems. Where you probably see that the most is an SCR. There's a lot of SCRs. SCRs could be controlled via 0 to 10, could be milliamps. They could also be pulse width. And SCRs themselves, so a solid state, or the silicone controlled rectifier, what makes an SCR what it is technically it is PWM signal to the voltage going to the heaters. So you could have a input reference that's pulse width modulation going into that controller, telling it, okay, I want you to run at 50%. So the pulse width is going to send a signal by sending pulses, and it's quite literally just that. It's a pulsing of the signal to generate a set outcome. You know, we want this to happen. So in the same way, that SCR heater is pulsing the voltage going through it to achieve the same result. Right? Ultimately, pulse width modulation is also entered into, say, mag bearing equipment. When you start talking anything mag bearing, we use PWM technology to create the control circuits and the magnetic fields we need in order to levitate those shafts and have magnetic bearing oilless systems. That is how we're accomplishing it. So this is something to really get familiar with, even if, so from my understanding, I'm not an expert in automation by any means, but PWM in terms of control signal used to be used more widely. Now I forget exactly which applications and why and all the good stuff about it, but it's not as common as it once was. On the other hand, mechanical is becoming more and more common. So this is, anyway, understand pulse width. Pulse width modulation is the same thing. It is an analog signal. It is an analog reference. So it is a variable thing to where we're talking, microseconds of pulses. And so the controls in here are able to cycle those pulses to where we say, for every, say, 10 micro or milliseconds, I think it's probably milliseconds, for every 10 milliseconds, we send a pulse of one pulse every group of 10. And if we wanted, say, 50%, we might send a 5 millisecond pulse of 10 milliseconds. And so we would send 5 seconds, drop 5 seconds, send 5 seconds, drop 5 seconds. That would be a very basic way that an automation system would utilize a pulse width signal. And if you try to put your meter terminals on that and read, you're going to see that meter just flashing. Which is also why if you're ever reading a output of a VFD, and it says it's outputting 30 or 40 hertz, for example, And especially if you do not have a true RMS meter when you do that, your meter is going to freak out in its voltage, and it's going to be erratic and all over the place. And that's because the exact same technology is what makes VFDs work. VFDs use a pulse width modulated signal to create the hertz that we're trying to simulate. It's all the same technology. We just use it in different ways. Your inverters, any inverter is using PWM technology, whether it be a VRV, whether it be Daikin Rebel systems, it doesn't matter. All of it is PWM based. Anyway, I'm not going to sit on that soapbox. Making sure. Okay. Any significant questions so far from anybody? No? We've covered our bases here. We will move on. So let's get into, we've pretty well covered a lot of the basics of, okay, this is an automation system, this is what things look like, this is how it works, yada yada. Let's kind of hone into each of these little components and what they are and how we can go about trying to troubleshoot them. So we'll start with our little actuator here. As I've stated, this is a 24 volt, 0 to 10 digital actuator. So we need to give this thing a signal. So right now, we have no signal obviously coming through. One thing is really nice about Belimo, and not everybody does this, and you'll see that even on the floating point, it'll have this same thing. That little black dial up in the top corner. That black dial is a rotation selector. So if I flip it, and it's just what, 1/8 of a turn is all it takes. Now I haven't done anything to change the input signal. I still have 0 volts DC coming in. But if you watch, I'm moving. And so that's what that black dial is for, is so that you can properly set what you want the rotation to be. Because that could be either reverse acting or direct acting. So in a direct acting system, you are increasing signal to increase position or flow. So at the inverse of that is you decrease signal to decrease position and flow. Well, a reverse acting is the exact opposite. You increase signal to decrease flow or position, and vice versa. So those are terms that date back to the pneumatics days. If you ever got into pneumatics or did anything on that end of the spectrum, you knew what reverse acting or RA and DA are. So if you ever walk up to a system and you see something that's got stamped on it RA or DA, and that's exactly what that's referencing. It is a reverse acting or direct acting. So keep that in mind. My point here, though, is say you don't have easy access to the automation system, or you're just trying to figure out, okay, this is a chill water valve, and they're saying it's not working. I walk up to it, it's in a set position that I want to see, okay, is this valve actually doing what it's supposed to do? Well, in our area, Belimo is extremely common, so more than likely it genuinely will be typically a Belimo of some kind. You can walk up and flip this little dial just as a real quick basic test. Now you got to put it back, right? It's not going to reset itself. You've got to be the one to set it back where it needs to go. But that is one really quick, easy way of testing. Well, one, is the actuator getting power, right? If it's not getting power or proper 24 volts to begin with, it's not going to function. If it is getting 24 volts and it doesn't rotate, Well, then it could be the motors in here have gone bad, the control circuit, or maybe the gears have stripped. Right? So if the gears strip out internally, you may hear the little motor in here spinning all day, but it's never going to actually turn. And see, these don't do it based off of time like a floating point would. So these are using its own internal, so this actually has a little control board inside of it, whereas the floating point didn't. This thing's pretty stinking stupid. It just, you put voltage to it and it turns. That's about it. Now, that's not the case on this. If we were able to get that open, there's a legitimate little control circuit in there with a processor that is making decisions based off of how much that input is reading, and at the same time, because you're going to have a constant 24 volts coming to this thing, at the same time, it is reading its own potentiometer to know what position it's in. So it's going to keep spinning until it registers that it has hit that potentiometer point. So just because you hear that motor start turning, my point is, don't just assume that the actuator is functioning. Make sure you watch this gear assembly and that it actually rotates. Because as you saw, that's pretty slow. And typically they are. They're usually not very fast. This one's rated as a 95 second. You can buy them at different speeds. A digital input, the speed is a lot less impactful. Now, it does play a part, right? And without going crazy into logic programming, the speed of this actuator is important to a programmer, because if his PID loop is calibrated to a different actuator, it can overcorrect faster than the actuator can actually respond to the signal given. And it will cause the entire control sequence to get very erratic and out of control to where it just bounces up and down, and it never actually locks in where it needs to. And that would be because genuinely, you walk into a controls shop and you need to replace this actuator because it won't spin, and this one's rated for 95 and he gives you one rated for 180. It's possible that time difference could be enough that this actuator won't turn as fast as the logic in the controller needs it to. And that can throw the whole thing out of balance. And that is extremely critical when you're dealing with floating point, because the entire thing works off of time. Now this has less impact on time, so if you walked in and he had it's not a real value, but say he had a 100-second actuator, he didn't have a 95, probably not going to be that big a deal. It's not going to throw the PID out that much. Could it? Sure. Will it? Doubt it. So ultimately, we can take, and this is where we get into signal generators. Now, this is a fairly cheap one. I got this on Amazon years ago, quite a few years ago, now that I think about it. There's two versions of this thing. The model of this is a JSVISG-MS. Oh, that's actually a pretty good idea. This particular one is by Utronics. Yeah, I can write that down. So I have used this one for a while, and genuinely, I'm pretty happy with it. I could recommend this one to you, but I'm going to warn you. There is two versions of this thing online. You have a nope. You have one with an internal rechargeable battery and one without. The one without does not take batteries at all. Hopefully y'all can read that. Yeah, it's coming through. So I personally have the one that has an internal rechargeable battery built in. I have the ability, either way that I choose to go, to either run off of the units 24. So for example, I could take the 24 that's being fed to this actuator, feed it into the voltage input ports on this signal generator, and then I can run a third wire to the reference port and then, control my valve. Or I can, when I turn it on, I can just run it off of battery, and the battery will send my voltage out that I'm looking for without having to have an external power source. If you get the other one, and I don't know what's different about the model number, but if you get the other one, you will have to have an external power source no matter what. Now, this is not going to be your permanent long-term signal generator. I've made this one work, and it works well. It does. But I do also recommend that at some point invest in a little bit better quality one. I'm trying to think of a couple of brands. Man, there's a handful of brands out there that are actually pretty decent, but they cost a lot more. I think I spent $60, something like that, on this one. Maybe a little more than that. But a more full-fledged one that's going to be a lot more user-friendly. This one, if I chunk it across that room and hit the wall, it's not going to turn on after that. You could go buy them, and yeah, they could take a pretty good beating, but you're going to, I think they usually run around $200 to $250 for a basic one, but again, a quality one at that. So anyway, that's my recommendation there. Let's get this bad boy going. So I'm going to rob this little wire here. Yeah, if anybody has anything in the anything y'all recommend in the chat in terms of a signal generator, now would be a great time to throw that recommendation in there. So I'm going to hook up to analog voltage outputs. I also have an analog amps, or it's AIO. So the I standing for amps, V for volts. I'm going to go ahead and hook all this up. Watch I go to do this and the thing blows up in my face because I did it wrong. Good content. All right. I'm hooked up, got my wire. Oh, turn the switch on. I'm set to voltage. Let me pick this up. So now, maybe y'all can see that. I'm going to ramp the volts DC. Well, I'm not seeing it change. All right, we get to do troubleshoot live. Why is it not changing? Give it a second. All right. Cool. All right, so in this particular case, let's treat this as a real scenario. I have 24 volts coming in. I can verify that. 24 volts AC. These can technically be AC or DC, but I am sending it 24 AC. So I can confirm that I have 25.4 volts AC. All right, so that's happening. Now I need to switch over to DC, and I should have a 0 to 10 DC. So I'm go over there. So I'm going to go from terminal 1. Terminal 1 is my common on this particular one, or my ground. I'm going to go to terminal 3. All right. So between those two terminals, I do not have any DC input. Now that could be because I was trying to skip a step. Yeah, I am outputting. Okay. I understand why it happened, and it's my own fault. When I hooked this up, I did not hook up the internal ground source, so I don't have an actual way to complete the circuit. I genuinely just did it out of curiosity. Normally when I'm setting this up, I have 2 wires running out in the field. This particular time I didn't. So you got to see that lesson live. We're going to go ahead and turn this off, and then I need to run a wire from ground to my ground over here, and hopefully the thing doesn't blow up in my hand. If it does, hope y'all really enjoy watching the process. Yeah. All right. Steal this wire here, get my strippers. Okay. Let's see. Wire this in first. Get in there. All right. By the way, I highly recommend this little guy. They've got newer versions of it. This is technically the older version, but it's the Klein 32581. This is a fantastic little thermostat or just control screwdriver. All right. Out of sake of safety, I am going to just tap it to it first in case something goes pop before I just actually throw it into the terminal. Oh, would you look at that? Nothing blew up. Ain't that disappointing? All right. So I'm going to actually tie this in the right way. I know everybody was taking bets on the big spark. Okay. So at this point, we're tied in. We're giving it 10 volts VDC. We've completed our circuit because, well, it takes 2 wires to complete a circuit, not 1. And we are spinning on the actuator. Now I can vary this down, and I'm going to go to just say 5 volts VDC. All right, right there. So I'm going to expect that once that gets up to the 5 volt position, it should stop. And there we are. It says that's 5 volts, or that's 50%. It's not quite 50%. Belimo makes pretty good stuff, so I'm going to trust the Belimo over my little thing here. Let's see. They're about right there. So once I got to 6 volts, that's a true 50%. Anyway, you get the concept. These things can be really handy in troubleshooting actuators. So I highly recommend everybody have some kind of a signal generator. Ultimately, the alternative, say you didn't have this, then you've got to have some form of way to work with the building automation front-end system. You get into the computer, be able to override that, whether that's, whether they have a remote ability, you got to call the engineer on the phone. However it is, it's just a much bigger pain. So if you're just trying to do a real quick basic troubleshoot and you want to verify that the device itself is doing everything it's supposed to, then a signal generator allows you to do that, and you have complete control of whatever is happening. So the more control you have in a test environment, the more pure the test you're making is going to be. Now, say we did all this, and I have full confidence in saying that this actuator has nothing wrong with it. It is not the problem. But it still will not actuate no matter what happens on the front end. At that point, I'm going to start asking questions about this guy. And so what you would want to read is between your common and your reference terminal, your reference input, is that controller actually sending any kind of control voltage to it? If the answer is no, don't just automatically assume this controller. So even if you read across there and you do not see it, take the time, go ahead and pull the wires completely off. Pull everything off. And then with it off, read between the common and the reference wires. And then see, okay, do I have the voltage I'm looking for? If the answer is yes, you've got a little bit of a dilemma at this point. Okay? This is where having a voltage generator does help, because what's possible is if the internals in here go bad inside the actuator, it can create some kind of short internally, so that your VDC coming out of your controller might read 0 because the actual current load on this is next to nothing. So it doesn't take a whole lot to pull that voltage down to very little to nothing. Right? But when you remove that off of whatever that load is that's overloading that output, now all of a sudden you see the voltage. So if your signal generator can hook up to it and modulate it, but the building controller can't, then it is very likely that it is actually the building controller. But if you do not have a signal generator when you're testing this and you're trying to only use the controller itself, be careful not to just condemn that controller, because you're talking, $1,000 or more to get one of these replaced and reprogrammed and configured, because these aren't as simple as just a plug and play. They have addresses, they have specific program features and functions, and there's a lot that goes into this that requires somebody with a laptop and some know-how. So this is not a small decision to say that any one of these is bad. So in a perfect world, if you did not have the signal generator, then my suggestion would be to go find an actuator or find something else and do the actuator first, right? So these actuators are, a few $100, right? Plus some of your time to change them, okay? A lot less cost than this. Or maybe you go find an actuator in the same building that is working. You can confirm it's working, so you trust it. Pull that actuator, go over to the one you are working on and plug it in. Right? Or I say plug it, wire it in, whatever. Right? You don't have to actually mount it on where it needs to go. Just move the wires and wire it up. Does it actuate? Because if you can wire that controller into a different actuator and then it does what it's supposed to do, then you've just eliminated that that actuator is the problem, not the controller. Obviously, you wire it into both of them and you trust this one and it works on neither, well then yes, you have a bad output, but. Just because you have a bad output on one of these controllers does not mean you condemn the controller. Because we get to decide what output does what. So this isn't a factory controller that we have absolutely no functionality to do anything with. So at that point, the building's control people, or yourself if that is you, can hook up and just reassign the output. So say you have 5 outputs or analog outputs on that controller, and output 3 is the one malfunctioning, but output 5 is open and available and not being used. You can just go into the logic blocks and reassign that output terminal, and then just move your reference wire over, and you're golden. You don't need to replace it, and you can put something in there or make a note in the controls, whatever. There's things you could do to notate that output 3 is bad without having to spend $1,000 or thousands of dollars to change a controller out. And all the time and pain in the butt headache that is. Yeah, anyway. Any questions on that? That was a lot, honestly. Okay. All right, so next, I'm going to take this floating point. I'm going to take this 24 here. I'm going to try not to short it. I'm just going to show you what can be done. All right, so floating point, I've got 24 volts here. And I can just go to terminals 1 and 2. And I start to actuate. And right now, so terminals 1 and 2, I am spinning clockwise. And then, so the control system would know, okay, so I want to open X%. I'm going to send I've got a 95-second actuator. I'm going to send 24 volts for X number of seconds, and I'm going to get that percentage. Now, I do not have a reference or anything else. So there's no potentiometer. So I have no idea what position it's actually in. I can only calculate that position based off of how many seconds I send the signal. Now, let's say I opened it too far and I want to close it and I want to turn counterclockwise. Well, then I go from 1 to 3 and just give it 24 volts through my little DC relays or just my little cube relays. And now I'm spinning the other direction. And it's literally quite that simple. If you want to see a more direct result and kind of watch the whole process, get my little flyaway there, I can go from 1 to 2 on here. And now you're not going to be able to see it, but that's okay. My little motor right here is now spinning, and that's just spinning the gears and going up there and turning the main thing. Now I could do an entire class just on actuators alone. Ultimately, just kind of an interesting gee whiz with it. There's a whole gear assembly inside of this thing that makes it function and operate. This motor, when you hear it, clicking or it comes to the stopping point, so when it torques out on a floating point, there is a clutch inside of here, and it is it's a magnetic clutch. So what that means is, I'm trying not to shock myself here in a bit. What that means is that when it hits the stopping point, so it rotates all the way over and it stops, that motor is still going to be spinning for as long as that 24 volts is there, right? If it didn't, then you'd have a lock rotor condition, right? How it's able to spin, we can't turn any further, is because on the end of that shaft, there's a little bitty magnet that sits inside of another magnet, right? So imagine just a cup with a round rotor. That rotor is a magnet, the cup is a magnet, they magnetize together. So as the motor is spinning, it's causing the cup to spin the gears. All right? So as once the gears hit their stop point, they can no longer turn, but the motor can keep spinning because the only thing in between there is a magnetic field. But there's no actual physical connection or tension point that's going to create an issue. So just kind of a cool little thing there. I'm not going to get any crazier with that. A lot of controllers, especially, all these are some form of a VAV controller. A lot of them do have built-in actuators. So you can see on this Johnson Controls one, this is your actuator down here. This is where the damper shaft, this little red knob is your clutch. On your Distech, there is a clutch, and it's actually on the front panel here. You've got that little button, sticks down, goes down into here, and it is actuating your actuator there. So it's literally a controller mounted to an actuator. All of these are going to be floating point style. One of the most common issues I run into with floating point actuators is their lack of calibration. So one of the first things you can do when you begin to question, okay, so why is this not opening or whatever, right? So you go to the front end and it says that, okay, well, this damper is supposed to be at 100% position. You walk up there and it's actually more like 50% position, okay? That would be an immediate opportunity to say, okay, well, we may have a calibration issue. The vast majority of controllers, when you power cycle them, so that means you're going to shut them down for at least 30 seconds, preferably maybe closer to 60. Let that whole control circuit de-energize. Then you're going to boot it back up. They usually will go into what is known as a sync mode, or an actuator sync, calibration sync, damper calibration, whatever. That's the easy way to do it, but not all of them actually do that. So you will walk up to some where that feature is not built into the logic of these controllers. In that particular case, the only option you have is to do it manually. So there's two ways of doing it. So if you already know, okay, I'm supposed to be at 100% and I want to calibrate this thing, well, then just hit your clutch, drive it to what should be 100%, and then see if the automation system will react in such a way and begin to close it back down. If you have fairly open access to the automation system, you can just go in and override. So say it wants to be at 100, it thinks it's at 100, it's not at 100 though. Tell it to go to 0 and override it on the automation, and then just stand back, and you need to give that actuator the time that it actually needs to actuate fully. So if it's a 180-second actuator, if you don't give that thing, what is that, 3 minutes? 180. Yeah. If you don't give that actuator 3 minutes to completely actuate, or even if they're 90-second actuators, right? That's still, what, a minute and a half? Yep. It's really easy to be impatient with that. So if you react too soon and that controller hadn't finished actuating this thing, you didn't accomplish anything. So my rule of thumb, when I walk up and I've got floating points in the building, if I'm going to do a calibration manually through the automation, I will do the override, and then I will put a timer on my phone for at least 4 to 5 minutes. 4 to 5, not 45, 4 to 5 minutes. That way I can have full confidence that it finished doing whatever it needed to do. And then I will drive it the opposite way. So if I went from 100 to 0, I'll go back from 0 to 100. And the whole time I want to be monitoring this actuator and verifying that it's actually making that full turn from that full 90-degree spin. And a lot of times what can happen is the gears in these are plastic. They inevitably break. They hit a weak point. And you'll start to hear this thing click, 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 click. That is an indicator that you have bad gears and they need to be changed. Now, when those gears are on the edge of failing, or you have an actuator that is constantly having calibration issues, it's usually because you've got a gear issue. And so every 4th, 5th, 10th gear will slip. And so every time that gear slips, you get further and further out of calibration. So just keep that in mind as you're going through these. Floating point, calibration, major issue. Digital, calibration is not so much an issue because, well, it's actually smart enough to know what it needs to do. Let's talk about temperature real quick. Yeah, I'm watching that. So there's a couple of different ways of controlling space temp. You can have a wall sensor. This one actually has the ability to have it's got a rheostat, so that's what this little dial here is, and you're able to vary the request, right? So they can adjust this on the program to where dead center would be 0, and you can have, like, say, a -2 degrees or positive 2 degrees. So that would mean, so if set point was 70 degrees and they had a 2 degree plus minus span, then the tenant could adjust that from 68 to 72. And dead center would be their 70 degree set point. So, and that could be any number of things. You know, that is fully programmable in how that functions and if that's used. Now, this particular wall sensor is network based, so it doesn't have, you know, any kind of control wiring. It's just it's got an Ethernet port that, or I guess that'd be a Cat 6, I think, Cat 5, Cat 6. Anyway, it plugs into it. And that is going to run up to the controller, like right here, and plug in. And you can read on the on there, it's going to say T-stat. Okay, that is the port at which this is going to hook up. Now, typically these are a little bit fancier ones, so you've got the adjustment in them. They can usually do, or they can do temperature. And sometimes they can do even humidity. Now, this particular one, the sensor used to be right there. It has since been broke off. So there's no telling what happened to that. Ultimately, when it comes to troubleshooting this, is it reading accurate, first of all? All right. So you put your own, you know, temp probe on there, set it up. You know, and is what you're reading right here at the stats actually what the automation is displaying? Okay, so there's one test. If the answer is no, so say you read 70 and this says 75, okay, then you need to verify that it's not the controller or logic causing the issue and it's actually the module here. So the easiest solution I could recommend is either the customer have one, you have one, or go take one that you do find is accurate, pull it off the wall, unplug it, take it to where you want it, plug it back in, and then see, does the other module that you already verified was working across the room, or maybe, you know, across the office, whatever, is doing the exact same thing. So if they both read identical, then it's likely a logic or could be a cable. You know, if the cable's got a weak point or some kind of resistance being generated in it, that can give a false reading. Or it could be just the input on here. Maybe it's not logic, maybe it's not anything else. It's just the where the cable plugs in just isn't good anymore. The physical input has failed. So ultimately, if they did read different, so say you did the swap and they read, you know, the new one read properly, then yeah, obviously change out the wall sensor and you're good to go. Now, then you get into the really stupid ones. These are my favorite. It's just a thermistor, end of the day. That's all it is. It's just a little bitty thermistor. These are typically a 10, this is Honeywell, so this would be a 10K type 2. So if you don't know, there's multiple types of resistance charts out there. Most of your Honeywell and Distech systems are using a 10K type 2. And I think Johnson is using a 20K, if I remember correctly. We have a 20K here. Yeah. So, I don't have the tag. Anyway, if I remember correctly, I could be wrong. Somebody knows, they can throw it in there. 20? Okay, so that Honeywell's 20. Some of them are 10, some of them are 20. It could be either or. It is important to know which. So the difference being, a 20K means that at 77 degrees, that thermistor is going to read either 20,000 ohms or 10,000 ohms. And then when in terms of your 10K type 2, so it could be type 1, 2, or 3, the difference in the 1, 2, and 3 is the range at which the ohms change. So, for example, 111 degrees on a type 2 is 4,561 ohms, whereas a type 3 is 4,847 ohms. And those 300 ohms is enough to, I mean, that's a significant change in temperature. So that's going to throw off your calibration and if you're using the wrong chart. Anyway, as a technician, you're trying to troubleshoot this, these Honeywells are actually removable. So we can take and pluck this little guy out. And let's just say this tiny little booger goes bad. Ultimately, pull it out, get a new one, stick it in, and you're probably fixed. You don't have to do anything with a wall plate. You don't have to change any wiring. That's it. Now you need to know though, what kind is in there when you do that. You got to know, is it a 10K? Is it a 20K? You put the wrong one in, it'll never work right, obviously. But these are just a 2-wire. So this would be a analog input device. So the controller is doing nothing more than just reading ohms through that thermistor, and then it's converting that into a temperature via the chart, and off we go. Front end gives you a temp. Same exact thing that is happening here with these. You just 2 wires. This would be one that could mount on water. You could mount this on duct. Typically this style, this is a Johnson setup. This would be something you'd see on like ductwork a lot. This one could be duct or water. So yeah. Ultimately, they're thermistors. Just pay attention to their ranges. You troubleshoot them like you troubleshoot a thermistor. You use your calibrated one that you do trust, and compare, and they should either match up or they don't. Word of caution when you're using little cube relays. So this particular one is a single pole double throw. So we have input on terminal 9. Terminal 5 should be your normally open, which it is, and then terminal 1 is your normally closed. And then these 2 little tiny terminals, 13 and 14, sitting beside each other, that is your coil. Now these will tell you, like this particular one says that at 120 volts it can do 7.5 amps, or at 240 volts it can do 7 amps through those contacts. And while that is true, it will do that amperage. My experience, it won't do it for as long as you want it to. Okay? Typically we put something in like this, say it's running just a little small heater of some kind. Okay? Or even just a motor. Maybe you use this to operate your blower motor. Okay? These don't last very long. I don't know why. It's just the way they're designed, the make. Maybe they're just too cheap. Maybe the material they use. I mean, and sure, you may get a couple of years out of it. Maybe. You might only get 6 months depending on what you use for it. I do not use these to control loads. We want to use these as pilot duty devices, not load duty. You want to, so at that point, you know, my recommendation is use this to control. So you don't want to hook your contactor coil straight to those triacs, because they're not going to appreciate that, because then you're going to start burning controllers out. But at the same time, I don't want to run my heater or my fan through this contact either. So I'm going to feed from the controller to my coil on the ISO relay. And then my ISO relay is going to control the coil on my actual contactor and or relay. You know, one that's, was it the 430, the 430? 430, 930, maybe it's 930 series. Anyway, the brown ones, or the little black, like peanut style, little cube looking relays. They've got a termination number. I forget the exact one off memory. Anyway, that's my recommendation on this. So if you're walking up and you are finding these are failed, and they're trying to run actual loads through this, whatever the load may be, I highly recommend you consider talking to the customer and seeing if they would be willing to turn this into an ISO, and you rewire that circuit to have an actual contactor or something else that'll handle that load better. Let's see here. For those who may not be familiar with them, this is a spring-loaded actuator. These are real common to see, honestly, just a lot of types of systems. Probably the most common on like fire dampers and things. So this particular one is 120 volt. Yeah, 120 volts. So we just feed between the black and the white, 120 volts to this, and it's going to open this actuator. And as soon as that 120 volts is dropped out, the spring in here is going to just close it back. And it's really that simple. So this could be hooked up to a contactor, and this could be controlling, say, an outside air damper that is just open or closed. So when the system is in occupied and is needing to run, and we need to pull in outside air, then the controller can fire the ISO relay, which then fires the control relay for this actuator, and we're able to open the outside air damper up and make it function for the mechanical room air handler. And when we're done, we just drop out the coil voltage and it closes. We don't need anything else. And all we needed at that point was one binary output. Whereas, I guess technically we only need one binary output with this, but a lot more wiring goes into this. This thing's a lot smarter, a lot higher failure point. The other factor is this loses power, it doesn't close. In a fire situation, you need any air source to be able to close. That's why they use these on fire dampers to begin with. And same way, if you have an outside air damper of any kind, I do recommend having some kind of spring return on that. Granted, some systems we put in now, we modulate that outside air based off of different conditions, but even if that was true, we're still going to have a true fire damper on that outside air input. Anyway. What else can I break? Oh, something really important to touch on. Each one of these controllers has these little nipples on it. These things are static pickups. Usually, like in this one, this Honeywell, you'll see a triangle, which is a symbol for a delta, which means difference, and a P, so a delta P or differential pressure, and then a plus and minus. So this is going to hook up to some kind of static pickup ring inside of the ductwork. So on a VAV specifically, or a fan power box, that is going to be what is monitoring how many CFM you're flowing through it. This Johnson controller is there. Distech, they've got them back over here. So usually you'll have some kind of poly tubing running from the controller to the inlet of the fan power box or the VAV box, whatever it is you're using. And there's some really critical things to keep in mind. Ultimately, it's really easy to get these backwards. So, you have your, we'll just stick with something basic on a VAV. Here's that. You've got your round collar sticking out, and you'll have two little ports. All right, air is moving this way. Now, memory serves, your top port is going to be your high port, and your bottom port will be your low. And there is an actual ring, and it can look a couple of different ways. It could be just a circle, or maybe two circles. I know maybe it would be, with just the pickups coming off of each one. So you have like an inner circle and an outer circle. That's one style. You could also have a cross X style. So one would be the high, one would be the low. So either one of these, flip a coin as to which one it would be. I'm not going to say one's more popular than the other, at least not that I've noticed. Anyway, the difference is the one closest to the inlet air is going to have little ports in it. Little bitty, change colors here. Have little bitty pickup ports. And its primary job is to read, oh, I did that wrong, either way. Its primary job is to read total static pressure. Okay? Total static pressure is static and velocity pressure combined. Okay? So we can't necessarily read velocity pressure, but we can calculate velocity. The second ring, or the second port in the X, the tubes or the openings are going to be on the back side. They're going to be on the other end of the air. Those are your static ports. So the one on the front side is picking up not only the velocity, but also the duct static. The ones on the back side are picking up strictly the static. The velocity pressure is not shooting into the little holes. We're able to take those two pressures and the difference between them and chart them on a graph. And a lot of your VAVs or fan powers, you'll see this little weird looking kind of bar, or not bar, but line graph on there. It looks typically pretty strange. And it'll have like just a straight line across with CFM and 8-inch, 10-inch, whatever sizes. That is your flow chart for the box. And those are pretty universal. How we're getting the reading to read that graph is through this. So if these don't pick up properly, they could get clogged. These sensors could just fail. Those are probably the two most common things. Either the sensor pickups just go bad, or the rings themselves get full of dust and clog up. Then they're not going to read CFM properly. So that could be affecting why the actuator is not adjusting properly. depending on how they've got it configured and everything else. So you have to pay attention to these tubes and hookups, and I cannot tell you how often I find them backwards. If you're struggling to get the readings you're looking for, you might really try to verify. Now, don't take I have ran into them where the high port was the other way around. So don't just assume that every single one of them, the high port's going to be on top. Just a word of caution there. So, another critical thing that really affects this, and it's kind of crazy. This is typically a round duct, hard metal. Depending on the size of this, and I'm actually, if somebody can remember the ratio, please post it in the comments. But there's a ratio to where, let's say this is a 10-inch round input. Okay? I think it's a multiplier of 6. So it'd be what, 60 inches? It's something, there's a multiplier you put against that. And that multiplier tells you how many feet of solid ductwork is required before it, as it comes into the box. So, for example, if you needed 6 feet of minimum hard pipe, but you only did 2 feet, or maybe they say they didn't do hard pipe at all, and they ran straight flex directly to the back of that collar. These pickups will never function properly, period. The reason for that is the flex duct has a spiraling feature in it. And that spiral creates a significant amount of turbulence on that airstream to the point where that turbulence just completely throws those pickups haywire. And they can't register properly. So since they can't read properly, you'll never be able to get them to work. And whatever readings you have on your computer are just, they're useless. So be very careful with that. Many times, a lot of the time where I see people do this, that's something that happens during the install itself. I see people do this because they don't have enough space to do it the right way. So instead of making adjustments to fix it and relocate things, their solution is we're just going to flex duct to it. It's not going to work, especially if the system is trying to monitor CFM and use that in any kind of way. The point of the hard pipe is if you use the ratio properly, again, I'm sorry, I'm not specifically remembering it off of memory, but if you use that ratio, it's enough length of hard pipe that it allows that airstream to stabilize and all that turbulence to be taken out of it enough that those can pick up properly. And that's the whole point as to why we need to do it that way, is so that we can read our CFM. Yeah, there's your basic field devices, actuators, relays, controllers, different types of components, using signal generator, thermistors, inputs, outputs, pickup tubes. Any final questions before we check out? Otherwise, that will complete this month's training. For those who are joining us online and are not APS employees, this is something that we do every month. This is a routine thing. We are hoping to expand this even further in the near future. But as it stands, as we do 2 classes a month, we have been doing this through internal systems up to this point. So typically the classes that I've been posting, that is what these classes are. Ultimately, we're testing it out and we're seeing how much more we prefer the YouTube live version. So the benefit to that is y'all have full open live access to what's happening here. Part of the point I'm getting at is we are hiring. So if anybody is interested, feel free to go to the aps-centraltx.com, and then we have a join our team page. Go to that, click on the link, put an application in, or send us an email, whatever works better for you, or just shoot us your resume. And you know, we'd really like to talk to you about possibly coming and joining our team and being a part of what we're doing here. So we have roles open all the way from upper level senior chiller techs down to just bare bones apprentices. So we take apprentices straight out of school, no field experience. We put them with leads out in the field, and we have a 2-year process that we put those guys through to try to convert them into full-fledged service techs. So if you know somebody or if you're interested in something like that, feel free to put your resume, application, whatever you have in, and we'd really like to talk to you. Other than that, that is going to complete this class, and we will. That's right. Okay. I'm sorry, Frylock. Yes. So he's one of our San Antonio boys. We also are hiring in San Antonio. So I'm specifically in Austin, Texas. San Antonio is also needing senior level techs, especially. So if you are in either of those locations, or if you're willing to relocate, we do that. We help with relocation in that process. So there, I got you in there, Frylock. I didn't leave you behind. Appreciate it, guys. We'll see you next month.